So in this video, we're going to have an application example of the extreme value theorem, where we apply uh, finding a global min or max to a specific application problem, not just a generic function. So let's say that the cost to produce x thousand widgets, whatever they might be, is given by this cubic function, and that this is only valid when x is between 0 and 60. So that's 0 widgets or up to 60,000 widgets, because x is in terms of thousands. What production level would minimize the average cost? So there's several phases here. First, we're not minimizing cost, we're minimizing average cost. So the first thing we have to do is come up with the average cost function. So C bar is always going to be C of x, the cost for x widgets, divided by x, the number of widgets. That will give you the average cost per unit. So in this case, that's 0.001x cubed plus 3x plus 100 all over x. Now, we could, of course, minimize this function and use the quotient rule when we need to find a derivative, but that's going to be a lot of extra work. What I'd rather do is, just like how you can take two fractions like 2/5 plus 1/5, oops, not 5/5, 1/5 and get 3/5 by adding the two numerators together, right? You can also reverse that process. You can take 3/5 and split it into 1/5 and 2/5. We're going to do something a little bit like that, where we have a fraction where the numerator is made up of different components, different terms. We're going to separate this into 3 different fractions, all with the same denominator, so that if we wanted to, we could recombine them, given that we have a common denominator. Now for the first two terms, we're just going to reduce this. So, oh, I forgot the 1. 0.01x cubed over x becomes 0.001x squared, plus, now 3x over x, of course, becomes 3, plus, and the 100 over x, I'm going to rewrite that with a negative exponent as 100x to the negative 1 power. Okay, so now I have a relatively simple, not polynomial function. It still really is a rational function because of that negative exponent, but at least I've written it without a fraction. That will let me avoid the quotient rule. So now I want to minimize this. Now what I have to worry about is the interval that we were using was 0 to 60, 0 units up to 60,000 units. But you'll notice that 0 is no longer in the domain of this function. When you find an average, you can't divide by 0. How do you average 0 things? It doesn't make any sense to do that. So one option is to sort of abandon the extreme value theorem and instead use what's called the critical point theorem. I don't want to do that for this example. I want to say this instead. So the domain for this function is no longer 0 to 60, including both endpoints. It's 0 to 60, not including 0 as an endpoint. However, we can count, well, what's a reasonable minimum? What would be the lowest possible value for x? Well, if we were going to make one widget, since x is in thousands, this would correspond to 0.001 for the x coordinate. Now this, we have a genuine closed interval because you can make just one unit and average just one unit, or rather find the average cost for that. So that's our interval for this function that we're now going to minimize. So since we're going to minimize this, and really I should probably move this out of the way a bit. There we go. Good. I need to find the critical numbers so I can then look for where the lowest and highest values are based on the extreme value theorem. So step 1, I'm going to find the derivative. F prime, C prime of x. I'll just apply the derivative to this formula, applying the power rule basically. So 0.002x plus 0 minus 100 times x to the negative 2 power. Okay, so I've found the derivative. Step 2, as we've seen in previous videos, it really has 2 parts. So the first thing is I need to look for where is c prime of x undefined. When I say where, I really mean for what x values. So within this domain, nowhere. The only place that this would be undefined is if x were 0. Why is that? Well, this can be rewritten as 0.002x plus 0, I don't need to write, minus 100 over x squared. And you can't divide by 0, so x cannot be 0. But as I said, that doesn't happen in this interval that we're using. We've excluded 0. We've moved the beginning of the interval up to 0.001 intentionally. So for the interval we're talking about, this would be nowhere. And whenever you want to use extreme value theorem, you have to have nowhere here. Because if there's any place that the derivative is undefined, the extreme value theorem is not going to apply. Well, there are exceptions to that. In this case, it applies because we don't have 0 anymore in this case. So now we can look for where is the derivative equal to 0. So I'll set the derivative 0.002x minus 100 over x squared equal to 0. Okay. And then there's probably several ways to solve this. I think it'll be easiest if we add 100 over x squared to both sides. So 0.002x equals 100 over x squared. I can multiply x squared on both sides. So I'll get 0.002x cubed equals 100. Next, I can divide by 0.002. So I'll have x cubed equals 100 over 0.002. This is the same as, I believe, 50,000, because the reciprocal of 0.002 is 500, so we get this. And then we can solve for x. X equals the cube root of 50,000. And of course, we do want a decimal approximation for that. Let me get a calculator real quick. Just take me a moment. So the cube root of 50,000. I get 36.8403. So there is the only critical number that we get for that function, that average cost function. So now, step 3, when I apply the extreme value theorem, because again, as I mentioned, we're dealing with a continuous function over a closed interval, we just have to check the endpoints and the critical number. So I want, what is c bar of, well, not 0, sorry, 0.001. What is c bar of 36.8403? And what is c bar of 60? Okay. So, going back here, we are going to be using, well, either one of these versions is fine, but I'll write out this one. All right. Oh, I'm sorry. Oh, I have a mistake here. Both of these should be c bar prime, not c prime. So I need to have a bar over both of these. Okay, so with the extreme value theorem, we are not checking in the derivative. We are checking in the original function. Any one of these are equivalent. We were just rearranging algebraically. We had not done any derivatives. So any one of these 3 lines is totally fine. I'm going to go with this one just because I think that will be a little bit easier. So 0.001 times, well, to start with 0 squared. Well, 0.001 times 0.001 squared, okay, and then plus 3, plus 100 over the input. Okay, well, this is going to be, well, 0. What will that be? 8? 1, 2, 3, 4, 5, 6, 7, 8. 0's and then a 1 plus 3. Plus, this will be a 10,000, no, 100,000, sorry, 100,000. So this is approximately 100,003. That decimal basically rounds down to nothing. Okay, so that is the average cost when you make one widget. $100,003. Basically $3 for the materials cost of the widget, and the 100,000 is all overhead, more or less. So when we try 36.8403, we'll have 0.001 times 36.8403 squared plus 3 plus 100 times 36.8403 to the negative 1 power. So the calculator I had is a little bit hard to use, so I'm going to pull up an online calculator because that'll be a little bit easier just to type the whole thing in. So 36.84003 squared plus 3 plus 100 divided by 36.8403. And I get 7.0716. This is in thousands of dollars, so you know what? Let's do this. 6.3. Well, you know what? Let's say it's in thousands. Let's just do this, too. That's fine. 7.072, because it's in thousands of dollars. We'll round to the nearest dollar. That's fine. So far, this is a lot lower than 100,000, right? And then C bar of 60, this would be 0.001 times 60 squared plus 3 plus 100 times 60 to the negative 1 power. So I'll throw that in my online calculator. And 60 there, and 60 there, and I get 8.267. So the lowest value is here at 36.8403 widgets. So basically that means in order to minimize the average cost, you should produce 36,840 widgets. Okay. Now, we didn't have to use a number line or choose test points because we had a closed interval. We can apply the extreme value theorem, and all we have to do is check the endpoints and the critical number, and that's it. So that's an example of an application problem doing a minimization, a global or absolute minimum.